Welcome! I'm Emily, she, her, hers, and shocker, today we're talking about relations, which maybe you figured out from the title of this. I'm going to first start off with what is a relation, and if you feel good about this part, just watch it at 2x speed, which you might be doing anyway. But then after this brief intro, just to get us all on the same page, I'm going to be talking about the 4 big properties of relations. They're super important to homework 9, and they're also on the midterm. So here we go. First we have the set A, 1, 2, 3. And we talk about a relation being on a set. And by that we mean that the relation is some subset of A cross A. So these are all the ordered pairs in the Cartesian product of A cross A. And a relation is just taking some of those pairs and sticking them in another set. Kind of fun. No, we could have a different set B. We could be taking A cross B instead, but a lot of times if you read the words in a problem, a relation on the set A, we mean it's a subset of A cross A. This isn't quite right, but we can kind of think about A being the domain and B the codomain. Those words are technically reserved for functions, but this does look very function-like if we draw out this relation here, like this. Actually, is this a function? Well, there's only one arrow coming out of this thing on the left here, right? Because if there's 2 arrows, that's definitely not, that would be bad. There's only 1 arrow coming out of 3. We are going to have an issue that 2 doesn't map anywhere. Not a good plan. So R as it is right now is not a function. It is a relation, but it's not a function. But maybe I'm going to just add in the pair 2, 3 into R. I'll go draw it over here. Now, does it seem like a function? Sounds good to me. Everything in the domain has exactly 1. Every input has 1 output. And also we could say, oh, this function is 1-to-1. So you thought you were done with that, but you're not. Okay, conclusion of intro to functions, or not intro to functions, but like their definition. And now these 4 big properties. Start with reflexive, which says for all x in A, or our domain, it's not really domain, the left side thing. For all x in A, we need x to relate to x, or I call them like same pairs. That's a very math definition. But let's look at some relations. So if we look at R on the set A equals 1, 2, 3, or A is the set 1, 2, 3. And R is the relation 1, 1, and 2, 2. These are both same pairs. Is R reflexive? No, R is not reflexive, and that's because we need every element in A to have its same pair in here. It's for all x in A. So now if we add 3, 3 into R, this relation is reflexive. And this relation is reflexive no matter what else we stick in here. So I could add in 3, 2, I could add in 1, 2. This is now a new relation. We could evaluate, is this relation a function? We could ask, is it reflexive? We could ask other things, but it is reflexive because it has these 3 pairs in it. Note, for problem 9 on the homework, maybe come back to this video. On problem 9 on homework 9, they talk about the diagonal relation. Those are just all the same pairs. So it would just be all of these but that is a side note. Okay. Moving on, we have more properties. Shocker. Symmetric, antisymmetric. And let's think about symmetric first. And maybe we think about this relation. In symmetric, the definition is saying for all x, y, which is for all x, y, where x is in A and y is in A in this example, because R is on A, is a subset of A cross A. So we're technically like need to consider every pair. But then if we look at the definition, it has this if statement in it that says, if x relates to y, then consider something. Well, do I need to think about, okay, when x equals 1 and y equals 2? No, it's not in our relation. So it's like x relate to y is false. False implies anything is true. So I don't think about symmetric in terms of kind of A cross A and looping over all of those, which is different than reflexive. Reflexive, we need to think about all the elements in A. But for symmetric, I tend to think about looping over all the pairs in the relation itself. So I need to ask the question, okay, 4, 3 relates to 2. Is it true that 2 relates to 3? Yes or no? Well, 3 relates to 2, and it's true that 2 relates to 3, so this evaluates to true. I guess I phrased that kind of weird. It's not 4, 3 relates to 2, it's just like, does true imply true? And then I need to look at the second pair in the relation and ask the same question. What does this evaluate to? It also evaluates to true, so check mark. This is symmetric. Note, I could have just thought about evaluating this double arrow thing. I don't really think about symmetric as a double arrow definition. I think about it just like for every pair, I need to look at the one direction arrow. And so I just like split it up. Right, this is the same thing. It's just, I wrote them, I split it into the 2 parts. Yeah. Okay. So that's symmetric. And let's think about antisymmetric. I do the same kind of work for this, where I'm going to think about pairs in the relation instead of, all possible pairs in the Cartesian product. Even though this needs to be true for all possible pairs, this has an if statement that's going to be false for pairs that aren't in our relation. So I don't care about them. So then I just start with this pair and I go, okay, well, I have 3 relates to 2. And now I need to flip, flip the y position, flip the x, and I ask, is this statement true? Well, for this relation, it is true and true. So then I need to continue and ask, okay, does 2 equal 3? Now, what does this statement evaluate to? We have true over here implies false. 2 does not equal 3. Okay, so this whole thing is false, right? Which means this is a counterexample. We don't need to do any more work. This thing is not antisymmetric. Okay, so that one's fun. Let's think about, I don't know, 2 relates to 3, and the pair 3, 3. Okay, and I just start with the first thing. So 2 relates to 3. I flip the positions. I ask, is this true? It's false. So I don't care about finishing the implies because false implies anything is true. It's kind of like if we had an if statement in C++, we don't enter the if statement. We just keep moving on with our loop, like keep moving forward. So I'm done. I'm like, okay, cool. This part is true. So this pair isn't going to be a counterexample. I go look at the next one. I go, okay, 3 relates to 3. And then I imagine flipping the y's and x's, but it looks the same. So I look at this statement and I go, okay, is this true? And it is. It feels weird, but it's true that 3 relates to 3, and it's also true that 3 relates to 3. So now I need to continue and go, okay, this part is true. So now, does 3 equal 3? Is this true? 3 does equal 3. True implies true, evaluates to true. So both of these pairs gave us true for the definition of antisymmetric, which means check mark, it's antisymmetric. Yay! Happy days for us. Okay, I have no idea how I'm doing on time, but one more, please stay with me. Transitive. And same deal as symmetric and antisymmetric. I'm just going to think about the pairs that are in the relation. I think that's why a lot of students struggle with the definition for reflexive, and remembering when we think about reflexive, we need to think about the set A. For the rest of these, I don't as much. But notice, like, we do recognize the definition is for all like triple pairs XYZ of things in A. It's just gonna be like, this part is gonna be false for pairs not in our relation. So the work we do to figure out transitive feels different than the kind of work we do to figure out reflexive. And that's okay. But just remember that they're similar. Anyway, I've probably said that way too many times. I'm really sorry. Okay, we got to think about something like, I'm just really reusing the same relation. I've written this thing like 4 times, and that's fine. Let's ask if this is transitive. So I just start with the first pair, and I go, okay, 3 relates to 2. And then I want to figure out everything that 2 relates to. So if I had another pair in here, I would kind of need to stick with this first element like a little bit longer to figure out transitive. Like, I'm not quite done with the pair 3, 2 right away. So I answer this question, what does 2 relate to? I fill this in, 2 relates to 3. So I come over here and I ask, does 3 relate to 3? This is the statement I need to evaluate. It's really hard to keep track of the X, Y's, and Z's, but notice these are the Y's, this is X, this is Z, so this comes over here. This is how I got this number. If this is tripping you up, I would just write on the side of your page, X equals, Y equals, Z equals, and then fill in the definition part. Okay. Hopefully you started to evaluate this. We get true, and true implies true, or does not imply true, implies false. There is no 3 relates to 3 in this. This is true implies false. That's a big no. So this is not transitive. Okay, well, maybe I want it to be transitive. So I'm going to slowly erase this. Whew, we did it. Okay. I'm going to add in this pair. Be like, okay, cool. That would have made the issues that the 3, 2 caused fixed. I said that wrong. I added 3, 3. And it fixed this transitive issue. So now this evaluates to true. And so now we can think about this element. I start with 2 relates to 3, and now I need to fill in everything 3 relates to. So I need to answer this question. What is something 3 relates to? And I can write 3 relates to 2. Actually, I'm going to start with 3 relates to 3. So then now what I need to evaluate is 2. This 2 relates to 3. This is the statement. I need to evaluate its truth value. And 2 relates to 3 is true. 3 relates to 3 is true. And 2 relates to 3 is true. True implies true. Yay. So this still might be transitive, which also means we got to keep working, which is kind of unfortunate, but that's fine. We're still not done thinking about the second pair, because 3 also relates to 2. So then we need to evaluate, does 2 relate to 2? And this is false. So we're still not transitive. This idea of trying to add in pairs to get to be transitive and making sure it works happens in Warshalls. You'll have to do that in the homework. But some quick reminders before I go. Closures are not on the second midterm. Asymmetric, reflexive is not on the second midterm. Warshalls is not on the second midterm. So some of those things you're going to need for this week's homework, but not midterm material. And then my other comment I want to make is that, it might have felt pretty good working through these properties with these nice pairs of numbers. And like if you look at homework 9, a lot of the relations are weirder, but it'll be okay. My advice is to, when you get to like problem 3 on homework 9, just write out some examples of pairs in the relation. Like you can't write out all of them, but give us some pairs to work with, and then think about, if I come up with the pair A relates to B, could I write anything that B relates to? And like we can like bring this weirder math problem down to a smaller relations numbers problem that it's easier to see and work with. So it'll be okay. It looks, homework 9 has like some weirdness, but we'll get through it. We know how to do it. Or we'll learn how to do it, I guess. And that's all I have. I hope this video wasn't too long. I'm sorry. Apologies. I'm out. Bye. I'm not out. I didn't pause it yet. There we go.